Hello everyone. Today we'll study the differential coefficient. So uh, let us understand first what is differential coefficient. For example, this is a curve of any function f of x. So uh, you can see here the values of the functional values of f with respect to x is changing uh, with the with the different values of x, right? So this curve is actually an increasing curve, and here we have different values of x with respect to x. Okay, so here you can see the values of f is actually changing, right? In different x, different values for x, we have different values of this f of x, right? So this is the axis of f of x, and this is the axis of x. While x is changing, we also have got different values of f, right? So as long the values are changing here, so it has a rate where the values are changing. The values of the functional values are actually changing, and this has a particular rate. So to determine this rate, I mean the rate of change of f of x with respect to x is actually the differential coefficient of that function. That means with the solving method, with the mathematical method of finding differential coefficient, we can actually find the rate of change of any curve with respect to that particular axis. Okay, so let us look at the definition here. So here you can see that the derivative or the differential coefficient of any function f of x, where you must remember that this f of x should be a continuous function. F of x with respect to x is actually a limited value of limit x tends to 0 f of x plus h, or you can say del x minus f of x divided by del x. Okay, so this is how we can actually determine the differential coefficient of any function f of x. Differential coefficient is has actually another meaning, which is the first derivative of any function f of x. So while we actually find the first derivative of f of x, we actually can determine the rate of change in any function, any function. Okay, so we understand that with the technique, with the solving technique of f of x, we can actually determine the rate of change of any function f of x. Okay, so let us look some example with the differential coefficient. Okay, so here we actually will determine the differential coefficient. Here this problem is actually solved for to determine the differential coefficient of any constant. Okay, so let us look how we can solve this problem. So at first we define the function f of x, which is equals to c, where c is a constant. Here we want to determine the differential coefficient of any constant. Therefore we actually initiated the problem with f of x, where we determine this f of x as c. So while f of x is c, we can determine f of x plus h, because to determine the differential coefficient we need to solve this equation, which states limit h tends to 0 f of x plus h minus f of x. Here h is actually actually the smallest part. Wait a second. H is actually, if this is x1, this point is x1 and this point is x2, then actually h will be the difference between x1 and x2. That will be the smallest part of axis is actually termed as h. Okay, so you can also call it del x. We're actually using h instead of del x. Okay, so as f of x equals to c, we can also determine f of x plus h, which will be actually equals to c, because if f of x is a constant number, remember the property of a constant number: the constant number will not change with respect to any particular variable. So if it changes, then that number will not be no longer constant. So the main property of constant is the value of that instant is actually always same over the any variable. It is x, it is time, or it is distance, whatever it is. While the term is constant, the value should be a particular value. Okay, so as long f of x is equals to c, which is constant, therefore f of x plus h should also be equals to c. Okay, so now we can determine the differential coefficient of f of x, which is termed as f prime x. As long you remember that initially we termed that the differential coefficient is the first derivative of any function, and we can also express the first derivative using f prime. Okay, so f prime x means the first derivative of the function f of x, which implies the differential coefficient of f of x. Okay, so f prime x can be defined by limit h tends to 0 f of x plus h minus f of x divided by h. Here we'll put the functional values of these two terms, which are c. F of x plus h is equals to c. F of x is also equals to c. Therefore this becomes c minus c divided by h. C minus c is equals to 0, so 0 divided by h is actually 0. So 0 divided by h is actually 0. Okay, that means the differential coefficient of any function comes out as 0. It also has a literal meaning, which is if any function is constant, then the value will be same over the time, over the space, or over the any variable, right? So c here is constant. As long as c is constant and it has a particular value and which is not changing, that means the rate of change of that function should be 0. If the rate of change is 0, that means the value is not changing, right? So we can also literally determine that the differential coefficient of any constant is actually 0, and here we have mathematically derived this situation. Okay, now let us look at another example where we'll actually determine the differential coefficient of the product of a function and a constant. We'll find the differential coefficient of the product of a function and a constant. That means we consider f of x as our defined term, and which is equals to the product of a function and a constant. Again, we are actually determining the differential coefficient of the product of a function and a constant. Here function is phi x and constant is c. We actually initiated the problem with these variables. Okay, we consider f of x is equals to c phi of x, where c is constant and phi x is the function or given function. So as we have determined f of x with our desired term, now we can also determine f of x plus h. Here f of x plus h will be c phi of x plus h. Here we just replaced this x by here the function of x is phi x, therefore the function of x plus h will be phi of x plus h. Okay, so we just replaced x by x plus h. So this is f of x and this is f of x plus h. And this is f of x plus h. We have determined both the terms. Now we'll determine the differential coefficient of f of x, so which is f prime x, which is equals to limit h tends to 0, f of x plus h minus f of x divided by h. F of x plus h is actually c phi of x plus h minus f of x. Okay, so f of x plus h minus f of x divided by h. This is how we actually determine the differential coefficient. So let us look at the second line. Here we have put the c as a common term and take out from the limit. As we can took this c out of this limit because c is a constant, number one reason, and another reason is c is not dependent on h, where h is actually going to 0 and which will not change any property of c. Therefore we can also take c out of this limit function. Okay, so we have taken this c out of this function, and this becomes c limit h tends to 0 phi of x plus h minus phi of x divided by h. You can compare the whole term with our definition of differential coefficient, which is f prime x, which is equals to limit h tends to 0 f of x plus h minus f of x divided by h. So as long this is the definite term of differential coefficient, and we can compare this term also with our definite term, and here we can see phi instead of f, right? So we can call it phi prime x, right? By definition we can call it phi prime x. Therefore it has become c phi prime x. That means if we want to take the differential coefficient of the product of a function and a constant, that will actually termed as excuse me, there should not be any prime over here. It should be c phi of x. Okay, this will come out as c phi prime x. Okay, so ddx of c phi of x is equals to c phi prime x. That means if you have any function like 4x, you want to take differential coefficient of 4x, you'll take 4 out of ddx this way, and you can differentiate x as a whole. Okay, so you don't need, you can just take c out of the differential term, whether it is if it is in a multiplied form. This is the main thing of this problem. Okay, so if you want to take the differential coefficient of the product of a function and a constant, then you can take c out of the differential coefficient, and you can only just determine the differential coefficient of the function, then multiply this differential coefficient of with the constant c. Okay, now let us look how we will determine. Everywhere it is written determine, actually it should be determine. Okay, M-I-N-A it should be. Okay, just for the correction. So now we will determine the differential coefficient of by the way, this is actually a note of this note has been created by one of my students from last term. So I have found uh, uh, some spelling mistakes over here. While I will see this, I will take the note. Okay, anyway, so uh, now we'll determine the differential coefficient of sine x. Okay, so differential coefficient of sine x we want to determine. Okay, let us consider f of x equals to sine x, as long we want to determine the differential coefficient of sine x. Therefore we initiated sine x as f of x. Therefore we can also find f of x plus h. Remember, everywhere we at first we have determined f of x as our desired function. Then we determined the f of x plus h. Okay, so then we have actually initiated this this operation. Okay, So again, f of x equals to sine x, f of x, x plus h will be sine of x plus h. We just replaced x by we replaced x by x plus h. Okay, so differential coefficient of sine x will be termed by f prime x, which is limit h tends to 0 sine of x plus h minus sine x divided by h. This is sine c minus sine d. We can apply sine c minus sine d formula over here, and sine c minus sine d is 2 cos of c plus d divided by 2 into sine of c minus d divided by 2. Okay, by evaluating this function, we have got 2 cos of twice x plus h divided by 2 into sine h by 2. Okay, so we just taken this 2 in the numerator, from the numerator to denominator, and it has become h by 2. Remember one thing, the limit h tends to 0, sine x divided by x is equals to 1. Okay, limit x tends to 0. This is a note, is not provided here. Okay, while you are watching this video, please take a note that please take the note that limit x tends to 0. Write down this way: limit x tends to 0, sine x divided by x equals to 1. Okay, always this is true. Limit x tends to 0, sine x divided by x equals to 1. Okay, so will actually apply that conclusion of our limit function, and we have got limit h tends to 0, cos of x plus h by 2 into sine of h by 2 divided by h by 2. Here we can just multiply this limit h tends to 0 with both the terms, and we have got limit h tends to 0 cos of x plus h by 2 into limit h tends to 0 sine of h by 2 divided by h by 2. And you can compare this term with our note that we have already taken, limit x tends to 0 sine x divided by, just considering h by 2 as x, limit x tends to 0 sine x divided by x equals to 1. We can write that this whole term is equals to 1, and if h tends to 0, then this value will be 0, h by 2 will also be 0. Therefore we have got cos of x into 1, which is cos x. That means the differential coefficient or the first derivative of sine x is cos x. This is how you can determine the differential coefficient of sine x. Now we will determine the differential coefficient of cos x. Here we initiated the problem with our function f of x is equals to cos x. We want to find the differential, as we want to find the differential coefficient of cos x. Therefore we initiated the problem with f of x equals to cos x. Now we will determine f of x plus h equals to cos of x plus h, and the differential coefficient of f of x will be f prime x, which is f of x plus h minus f of x divided by h. Now we just replaced f of x plus h and f of x by the term cos of x plus h and cos x. Okay, now we will apply cos c minus cos d formula, and this will come out as sine of d minus c divided by 2 into sine of c minus d divided by 2. Sorry, sine of c plus cos c minus cos d is 2 sine of c plus d divided by 2 into sine of d minus c divided by 2. Okay, so we have applied this formula, and this is now just adding these two x's, and we have got twice x. We have taken 2 as a common, and we just divided this by the term these 2, and we have got x plus h by 2. Okay, and here we have got minus h by 2. Okay, just do the fractional addition here. You will get x plus h by 2. Okay, now we have put these two over these two under h here, h by 2. Now we have got the function as sine of x plus h by 2 into sine of h by 2 divided by h by 2, and there should be a minus over here. There should be a minus over here. She forgot to put this minus. Okay, there should be a minus over here. What can I do? There should be a minus over here. Okay, there is a correction. There should be a minus over here. Okay, now you will get limit h tends to 0 sine of x plus h into sine of x h by 2 divided by h by 2 whole into minus 1. Okay, no problem, because sine of minus theta is equals to minus sine theta. Okay, therefore there should be a minus multiplied with this term here. Okay, now we just make these two parts with limit h tends to 0 separately, and here we have also got limit h tends to 0 minus sine of h by 2 divided by h by 2. We can take minus out of this limit function, and we will got limit h tends to 0 sine of h by 2 divided by h by 2, and this term will be 1. Therefore we will get minus 1 multiplied with minus 1 multiplied with this sine x, and this will become minus sine x. Therefore we can say that the first derivative of cos x will be minus sine x. Okay, okay, what will be the differential coefficient of ex? We can determine differential coefficient of ex with f of x equals to e to the power x. Therefore f of x plus h equals to e to the power x plus h. The first derivative, this is our formula for finding first derivative, and we replaced f of x plus h and f of x by e to the power x plus h minus e to the power x. As long as the x plus h has the same base, which is e, we can write e to the power x into e to the power h. Okay, so minus e to the power x, we can take e to the power x common from this function, and we have got e to the power x minus e to the power h minus 1. The Taylor series of e to the power x is 1 plus x divided by factorial 1, x square divided by factorial 2 plus x cube divided by factorial 3 plus so on. Therefore we just replace this e to the power h as the Taylor series of e to the power h. So this is the Taylor series of e to the power h, and we just put over the Taylor series of e to the power h minus 1, and this e to the power x, as long this e to the power x is not a dependent term of this h, that means here h is not the variable. That's why we have taken this e to the power x from this h function, from this limit function. We just taken out this e to the power x from this limit function. So again, this line will be e to the power x into limit h tends to 0, the Taylor series of e to the power x minus this one, okay, divided by h. So if h tends to 0, then this value will be 0, this value will be 0, and every value I'm sorry, we need to divide we need to rewrite this function with this term. Okay, here actually what she did, she just eliminated this one and this one, as long as this is 1 minus 1, so she eliminated these two ones from here, and this function has become h divided by factorial 1 plus h square divided by factorial 2 plus h cube divided by factorial 3 plus so on. And then actually here they the multiplied the whole this function with 1 by h. This 1 by they multiplied the whole function with 1 by h, and if you multiply the whole function with this 1 by h, it will become h divided by h, which you can eliminate these two h's from here, so it will become 1. 1 divided by 1 factorial is actually 1, so this is 1 plus h. It was h square. Now if you multiply h square with 1 by h, it will become h, so h divided by 2 factorial plus h, similarly h square divided by 3 factorial plus so on. Okay, so this is your new function for uh, uh, for from this function. Okay, so here if you put h tends to 0, the all the values depending on h here will be 0 except this value, this one, because 1 is a constant and it is not even dependent with this h here. Okay, so the whole term will become 1, and this one will be multiplied is actually multiplied with e to the power x, so it has become e to the power x into 1, and we'll got e to the power x. That means the differential coefficient of e to the power x is actually e to the power x. If you take the differential if you take the first derivative of e to the power x, you will get e to the power x. Similarly, you can find the differential coefficient of a to the power x, and this is the Maclaurin expansion of a to the power h. Will solve this problem with this problem with the Maclaurin expansion of a to the power x, and the Maclaurin expansion of a to the power x is actually x divided by 1 factorial ln a plus x square divided by 2 x square divided by 2 factorial ln a square plus h cube divided by 3 factorial ln a cube plus so on. Okay, so this will be the Maclaurin expansion of a to the power x, and here we actually but then we have multiplied all the terms with 1 by h here. Here h is eliminated, h square has become h cube has become h square this way. Now we have put h equals to 0 for all the terms, and we have got ln a divided by 1 factorial, which is ln a, and we have got a to the power x into ln a. You can do this problem as your homework, and you can send me your feedback. Okay, so let us look at the differential coefficient, how we'll determine the differential coefficient of ln x. Okay, so ln x, f of x equals to ln x, f of x plus h equals to ln of x plus h. The differential coefficient is h limit h tends to 0 ln of x plus h minus ln of x divided by h. Okay, so what they did, as long as these two are ln function, you can write ln of x plus h divided by x. Then you just find the you just solve this x plus h divided by x into 1 plus h by x, because you can write this function by actually you can say partial fraction, x by x, x by x plus h by x. So this is one method of partial fraction, and we can find h by x, sorry, h by x plus h divided by x is it can be written as 1 plus h by x. Okay, I feel a little bit of tired. Okay, no problem. So the differential coefficient. Okay, so you can multiply this, you can write this function as 1 by h into ln 1 plus h by x, and uh, the the Taylor series of ln of 1 plus h by x is basically 1 plus h by x is equals to x minus 1 by 2 x square plus 1 by 3 x cube uh, um, minus 1 by 4 x to the power 4 plus 1 by 5 x to the power 5 this way. Okay, so here what we have got 1 by h into h by x minus 1 by 2 into h square divided by x square plus 1 by 3 into x uh, h cube divided by x cube. Okay, so multiply 1 by h with all the terms, and you have got 1 by x minus 1 by 2 h by x cube plus 1 by 3 h square divided by x cube minus dot dot dot. Okay, so if h runs to 0, all the values depending on h over here will be 0. Therefore you have got 1 by x. So differential coefficient of ln x is equals to 1 by x. This is how we can determine the differential coefficient of different function. We have studied the differential coefficient of the product of any constant. We have studied that how to determine the differential coefficient of any constant. We also have studied how to determine the differential coefficient of sine x. We have studied how to determine the differential coefficient of cos x. We also studied e to the power x, a to the power x, ln x, and how to determine the differential coefficient of this function. So please practice, make a note of this lecture first, and study all these problems. And if you have got any difficulties regarding the understanding, then feel free to call me and contact me. Okay, so thank you so much for your attention today. Inshallah, we'll study the theorem in our next class. Thank you so much.